Okay, this video here is going to be going over the factor label method, which is in our first chapter of the chemistry book. The factor label method is very helpful for solving many types of chemistry calculations, especially those that involve multiple unit conversions. But I wanted to briefly explain to you how and why the factor label method works, and it's based on math. The first thing is that the factor label method makes use of multiplying by the number 1. So for example, if I started with the fraction 11 over 55, and I said I wanted to multiply both the top and bottom by 4, well, if you take a look, 4 divided by 4 is the same thing as 1. So actually, when I'm multiplying by 4 over 4, I'm just multiplying by 1. But there are times in math where that's helpful. Maybe I'm trying to get a common denominator and I have to be able to multiply by this. So if I go ahead and carry out the calculation here, 11 times 4 is 44. That's my numerator. The denominator is 55 times 4, which is 220. And if you used your calculator, you could verify that 11 over 55 has the same value as 44 over 220. In fact, they both equal 0.2. So there's the first example. Another one is making use of square roots. This is particularly helpful in Algebra 1, Algebra 2, and even a little bit beyond, is when you are simplifying things in algebra, oftentimes they don't like you to have a square root in the denominator. So we've got to be able to rewrite this fraction 2 over radical 7 into another form that's equal to this, but that doesn't have the radical 7 in the denominator. So what I'm going to do is multiply by 1. But instead of multiplying by the real number 1, I'm taking my square root in the denominator, and I'm just going to multiply both the numerator and denominator by that same thing. And any number divided by itself is 1. So radical 7 over radical 7 is just 1. But if I go ahead and carry out the multiplication, the numerator is 2 times radical 7. The denominator is radical 7 times radical 7, which is just 7. And so I was able to rewrite this fraction, 2 divided by radical 7, and I've rewritten it in another form that has the same value, 2 radical 7 over 7. And I did that by multiplying here by 1. Just like over here, I multiplied by 1. Okay, one final one. 1/2 is what I'm starting with, but this time I'm still going to multiply by 1, but the top and bottom aren't going to look the same. So what I'm going to do is I'm going to multiply the top by radical 100, the square root of 100, and in the bottom I'm going to put a 10. So the question here is this really 1? It doesn't look like 1. I've got something up top and I got something different down bottom. But if you take a look, the square root of 100 is actually just 10. So really what we have up top is 10, and what we have in the bottom is 10. So really this is multiplying by a 1, even though the top and bottom, the numerator and denominator, look very different. But this allows me to go ahead and carry out the calculation. 1 times radical 100 is 10. 2 times 10 is 20. And if you use your calculator, you can see that 10 over 20 is the same thing as 1/2. They both have a value of 0.5. So factor label method makes use of multiplying by 1. Next thing we want to deal with are what I call fractional cancellations. This is where you got fractions that are being multiplied by each other, and you're trying to cancel out common factors before you carry out the multiplication to begin with. So let's say I start with a fraction 11 over 6, and I'm going to be multiplying that fraction by 42 over 55. Now, we could go ahead and just multiply top 11 times 42, and then the bottom 6 times 55, and then try to reduce it, but those are going to be big numbers. If we can go ahead and reduce or cancel to begin with, it's usually easier to deal with. So, since my fractions are being multiplied, I'm looking for common factors in the top and in the bottom. Well, I know that 11 and 55 both divide by 11. So 11 divided by 11 is 1, and 55 divided by 11 is 5. I also notice that my 42 and the 6, they both divide by 6. So 6 divided by 6 is 1, 42 divided by 6 is 7. Now I can go ahead and carry out the multiplication. In my numerator, I have 1 times 7, which is 7. And in the denominator, I have 1 times 5, which is 5. So there is an example of fractional cancellations. We're canceling numbers, common factors. But the same thing is also true with unit cancellations. You can actually cancel units. So what do I mean by that? Well, let's say I'm starting with a piece of wood that is 6 meters long. And I want to divide it into 2 equal sections. So if I go ahead now and carry this out, 6 meters divided by 2, some of you might say, well, the answer is just 3. But 3 is only a part of the answer. This is not just 6 divided by 2, it's 6 meters divided by 2. So if I have a meters up top and I don't have another unit in the bottom to cancel it with, I have to leave it there. So the answer is not 3. The answer is 3 meters. So in this example, there were no units to cancel. But I could rewrite this in another example. If I started once again with that 6 meter piece of wood, but in this situation what I say is I wanted to divide it into sections, equal sections that are 2 meters each. Now, what do I have here? If I start with 6 meters and I'm dividing it into 2 meter sections, how many sections is that? Well, the 6 divided by the 2 is the 3. And if you go ahead and write meters, that would be incorrect. The reason why is we have meters in the numerator and meters in the denominator. They actually cancel out. Meter divided by meter is 1. Those cancel. So actually what I have here is 3 as an answer. Start with 6 meters, divide it into 2 meter sections, I can get 3 sections. Whereas my answer up here was 3 meters. There were no units that were able to cancel. So unit cancellation as well as fractional cancellations are very important in this particular factor label method. Okay, next, we also have to deal with unit conversions. For example, let's say I start with 36 inches. And I want to convert that into yards. Well, I know that 36 inches does equal 1 yard. So there's a very simple conversion right there. 36 inches equals 1 yard. But let's say I'm dealing with a situation that may have many inches, maybe several hundred inches. So I need a way to make a ratio out of this. So I'm going to show you both ways to do it. The first thing I'm going to do is I'm going to divide both sides by what's on the left side. So I'm going to divide both sides by 36 inches. Now, if I take a look at the left, I'm going to use my cancellations that we dealt with on the previous screen, our fractional cancellations and unit cancellations. I can see that 36 divided by 36 is 1. That cancels. And inches divided by inches is also 1. That cancels. So everything over here on the left side is actually just 1. So I'm just going to shift that over and say, write it on the right side, 1 yard over 36 inches is the same thing as 1. Well, I could have also done it this way. Instead of dividing, I'm going to rewrite what I started with. Instead of dividing both sides by the 36 inches, I'm going to divide both sides by what I started with on the right side. So I'm going to divide both sides by 1 yard. Now, if I take a look at the right side, 1 divided by 1, that cancels. Yard divided by yard, that cancels. So I'm not left with 0 over here. I'm left with 1, because anything divided by itself is 1. 1 yard divided by 1 yard is 1. So you can see I actually have two different ratios. I could write 36 inches over a yard, that equals 1, or I could write 1 yard over 36 inches. That's also equal to 1. And which way you want to write it depends on the problem itself. So what we're going to finish up here with is taking a look at a few different problems that we're going to solve with the factor label method. First one is, let's say we have 726 pennies. And what I want to do is convert that into dollars. Well, I need to have a conversion. I know that 100 pennies, and I'm going to abbreviate P for pennies, 100 pennies equals $1. But on the previous screen, I saw that we could write that ratio two ways. We could do 100 pennies on the top, with $1 on the bottom, D for dollar, or we could have $1 on the top and 100 pennies on the bottom. So how do I know which one of those two that I want to use? Well, it depends on the problem. The problem says we're starting off with pennies and we want to end up in dollars. We want to convert those pennies to dollars. So I need to choose a conversion factor or a ratio that will cancel out the pennies and leave me dollars. So the first step in the factor label method is you write what you start with. Well, the problem told us 726 pennies. P for pennies. And we always want to write it as a fraction. You can write any number as a fraction simply by putting a 1 in the denominator, and that doesn't change the value at all. So what I'm going to do now is I'm going to multiply it by my ratio, my conversion ratio. Well, I want this one. This will have a pennies in the denominator, $1 in the top, 100 pennies in the denominator, and this penny and that penny will cancel out, leaving me dollars. Now I simply just do the calculation. 726 times $1 would be the $726. Then in the bottom we have 1 times 100 pennies. Or excuse me, the pennies is gone. We just have 100. Then the final thing would do to do the numerical calculation. 726 divided by 100 would be 7.26. And I still have my dollars left over. So I converted 726 pennies into $7.26. Well, real quick, what would have happened if instead I wrote $1 over 100 pennies? What if I said I'm multiplying this 726 pennies by 100 pennies over $1? Well, what's going to happen here is the pennies in the top is not going to cancel with the pennies in the bottom. The pennies are actually going to be multiplied by each other. The P here times the P here, the penny times the penny. So this is actually going to give me 72,600 pennies squared over dollar. And that unit, penny squared over dollar, doesn't make any sense. So if you're not sure which way to write it, just understand that you're trying to eliminate what you're starting with. We're trying to eliminate the pennies, so you really want the pennies in the denominator. But if you put it in the numerator and you do the calculation and you see you get this bizarre unit over here, you know you've done something wrong. Okay, on this next problem, we're going to be converting miles to inches. We're starting off with 6 miles, need to convert to inches. So I've written down the two conversions that I need over here. The first thing I know is 5,280 feet equals 1 mile, and I also know 12 inches equals 1 foot. So factor label says you write down what you start with. So we have our 6 miles, and we always want to make a fraction out of it. So it's going to be 6 miles over 1. Then we're going to multiply it by our conversion. Well, we know 5,280 feet are in 1 mile. So I'm going to put the 5,280 feet in the top, and I'm going to put the 1 mile in the bottom. And what that does is it allows the miles over here and the miles down here to cancel out. If I go ahead and do the multiplication, 6 times 5,280 is 31,680. But I still have feet. The feet didn't cancel. So I have 31,680 feet on top and 1 times 1 in the bottom, which is just 1. So I'm not quite there yet. I'm out of miles, but I'm to feet. And we're after inches. So I need to convert the feet into inches. So I'm going to use that second conversion up there. I'm going to put 12 inches in the top, and I'm going to put 1 foot in the bottom. This allows the feet to cancel. That foot there cancels with that foot there. So if we go ahead and do the multiplication, 31,680 times 12 is 380,160 inches. And on the bottom, we just have 1 times 1, which is 1. So we could actually just leave the 1 off of the bottom if we would like. And our conversion gives us 380,160 inches. Final problem, and we'll be done with the video. We're going to do a little bit more complicated one. We're going to convert something that's given to us in kilometers per hour, and we're going to convert it over to meters per second. So I've written down the unit conversions that are necessary. I know that 1 kilometer is 1,000 meters. I know that 1 hour equals 60 minutes. And I know that 1 minute equals 60 seconds. So the first thing I want to do with is I'm going to deal with the numerator, the unit in the numerator, which in this case here is kilometers. I want to get from kilometers over to meters. Well, I don't have a direct conversion, but I do know that 1,000 meters is a kilometer. So if I go ahead and I multiply here, 1,000 meters on top times 1 kilometer in the bottom. The kilometers here cancel, and if I go ahead and carry out the multiplication, I will get the number up here. But instead of multiplying it out now and writing down that as an extra step, I'm just going to go ahead and leave what we have right now and just continue to write the additional conversions. And then I'll calculate the raw number answer at the end. So I've got 1,000 meters now. So I've got the unit I want up top, the meters, but I got to deal with my hours that are still left in the bottom. Well, I know that from my conversion that 1 hour is the same thing as 60 minutes. So I'm going to multiply by 1 hour over 60 minutes. And you can see that hour there and that hour there cancel. But I'm after seconds in the denominator, not minutes. So I'm going to go to my final conversion here. So I'm going to multiply this by 1 minute over 60 seconds. And as you can see, what that allows to happen is this minute here cancels out with this minute. So if we take a look at all of our units, the hour, kilometer, minute, all canceled in the bottom. The kilometer, hour, and minute all canceled here in the top. And that leaves us with the meters. I shouldn't say the meters canceled. The kilometers and the hour canceled and the minute canceled. The meter did not. So what that's going to leave me with is meters per second. And then I just need to do the math. The 120 times 1,000 divided by 60 divided by 60. And if you do all of that, you're going to get 33.3 with a line over it. So the answer here is if we start with 125 kilometers per hour, that's the same thing as 33.3 with a line over it, meters per second. And in this example and in the previous one, I did not deal with significant figures or anything like that. I assumed that everything was exactly true. That would give us an infinite precision, which is a separate topic. But anyway, that is the factor label method.